All right, let's get right into it. Today, we're going to crack the code on something that happens all around us every single second: chemical reactions. I mean, have you ever really thought about it? What's the connection between a campfire and cooking breakfast? They seem completely different, right? Well, it turns out they're both driven by the exact same incredible, fundamental process. And that process is what we call a chemical reaction. At its heart, it's just any time new stuff gets made from old stuff. Think of it like the universe is playing with a giant set of Legos. It just takes the same pieces and snaps them together in a totally new way to build something different. So, how in the world do we keep track of all this rearranging? Well, chemists came up with a kind of secret language, a shorthand called a chemical equation. It uses symbols you've probably seen, like H2O for water, to tell the story of exactly what's changing. And that is the code we're here to crack. Okay, so first up, let's talk about the single most important rule in this whole game, the balancing act. This isn't just a friendly suggestion, you guys. It's a law that keeps the entire universe of chemistry in check. But why, though? I mean, why do we have to go through all this trouble to balance things? What's the big deal? Is there some big secret behind it? Well, yep, there is. And it's one of the biggest rules in all of science, the law of conservation of mass. It's super simple, really. It just means you can't create or destroy matter out of thin air. Whatever atoms you start with, you have to end with. It's like a perfect accounting system for the universe. Nothing ever gets lost. Now, balancing might sound intimidating, but trust me, there's a simple little cheat code for it. You just follow these steps in this exact order. First, you count up and balance the metals on both sides of the equation. Got that? Okay. Next, you do the nonmetals. After that, you tackle oxygen. And last but not least, you balance out the hydrogen atoms. If you follow this order, metals, nonmetals, oxygen, hydrogen, it works pretty much every time. Awesome. Now that we've got the rules of the road down, let's meet the main characters. Turns out there are really 4 main flavors of chemical reactions, and each one has its own unique personality. First on our list is the combination reaction. And yeah, it's exactly what it sounds like. This is all about things coming together. You take 2 or more simple things, they react, and they form one single, more complex thing. Simple as that. And oh boy, does this one put on a show. A perfect example is burning a strip of magnesium. The magnesium metal combines with oxygen from the air, and it goes off in this brilliant, dazzlingly bright white flash. What are you left with when the show's over? Just a simple white powder. 2 different substances literally combined into one. All right, next we have the total opposite of that, decomposition. This is where you start with one complex thing, and it breaks apart into 2 or more simpler pieces. It's basically combination in reverse. And a really cool example of this is heating up ferrous sulfate. You start with these neat green crystals. As you heat them, they go on this little journey. First, they turn white, and then, as they really start to break down, they become a kind of reddish brown. And you'll even smell it. It gives off this distinct odor, kind of like a burning match. It's a total transformation you can see and smell. Okay, our third type is called a displacement reaction. The easiest way to think about this one is as the swap out. It's what happens when a more reactive, kind of stronger element comes along and kicks a weaker one out of its spot in a compound. And this is the classic experiment to show it. You take a plain old iron nail and you stick it in this beautiful, bright blue liquid called copper sulfate solution. And then you just watch. The stronger iron literally pushes the copper out of the way. You see the blue solution slowly fade to a pale green, and the nail itself gets covered in a new reddish-brown coating of pure copper. You can literally watch the swap happen right before your eyes. So how did the iron know it was stronger than the copper? Well, it all comes down to something called the reactivity series. You can think of it like a league table or a power ranking for elements. The ones at the top, like potassium, are the most reactive. They're the ones who are always going to win the fight and displace the elements below them. The ones at the bottom, like silver, are the least reactive. They're much more likely to get kicked out. And that brings us to our 4th and final type, double displacement. So if the last one was a simple swap out, this one is, well, it's the full-on partner swap. This is where you have 2 different compounds and they essentially trade partners. One of the most dramatic examples of this is when you mix 2 perfectly clear liquids together, like sodium sulfate and barium chloride. The second they touch, bam, A cloudy white solid instantly appears out of nowhere. The two compounds swapped partners, and one of the new combinations couldn't stay dissolved in the water. That solid is called a precipitate, and it's a dead giveaway that a double displacement just happened. So behind every single one of these reactions, there's another story happening, a hidden force, and that force is energy. The big question is, does a reaction give off heat and get hot, or does it suck in heat and get cold? Well, this gives us two final key ideas. On one side, you have exothermic reactions. These are the ones that release energy, usually as heat, and make their surroundings feel hot. On the other side, you have endothermic reactions. They do the opposite. They have to absorb heat to happen, which makes their surroundings feel cold. It's really just the two sides of chemistry's energy coin. And here's the really cool part. We've already seen both of these in action. Remember that dazzling white light from the burning magnesium? That's a classic exothermic reaction, releasing a ton of heat and light energy. But what about when we broke down the ferrous sulfate? We had to add heat to make it happen, right? That means the reaction was absorbing energy, a perfect example of an endothermic process. So we've cracked the code, we've met the main characters, we've talked about energy. But why does any of this actually matter outside of a science class? Well, the answer is pretty simple. Chemistry is, quite literally, everywhere. When you boil it all down, chemistry isn't just a bunch of weird formulas. It's the story of how our entire world works, how it changes and transforms, one single reaction at a time. I mean, just stop and think about it for a second. The food you ate for lunch that's giving you energy right now? Chemical reactions. The battery that's powering the screen you're looking at? Chemical reactions. It's all governed by these same simple rules we just talked about. And that really brings us to a final thought to leave you with. Your own body is basically a giant, walking, talking chemical factory, running trillions of reactions every single second just to keep you going. So think about that. What chemical reaction are you a part of right now?